So we defined the divergence in such a way that would help us with three-dimensional vector fields. So now we have to do the same thing with the curl. So the curl of a vector field is the cross product of the del operator and the vector field f. So that's going to be a bit more work here. So we're going to take our del operator. So a partial with respect to x, partial with respect to y, partial with respect to z. I'm going to have the cross product of it with f, g, h. All right, so I'm going to remind us how to do cross products. So we're going to take I, so this is the cross product, or the del with respect to x, and this is f, and this is j, the del with respect to y, g, and then k, the del with respect to z, h. And then I'm going to rewrite those two pieces over here, I and j. This is just a quick way to find the determinant for a 3x3 matrix, which is what we're doing. Okay, so I. You can see if we go forwards, let me do it this way. So forwards would be I, so the del with respect to y of h. So we're going to take the del with respect to y of h times the I component plus the j component. So that was I. J would be the del with respect to z of f plus the del with respect to z of, or excuse me, respect to x of g for k. All right, there's the first three pieces. Now we're going to subtract, and we have to do all of them in reverse. So the del with respect to y of f in the k position, plus, let's see here, the del with respect to z of g in the I position, plus the del with respect to x of h in the j position. All right, so let's put that all together. We're going to put the I ones together and then the j ones together and the k ones together. So this would be, all right, so the partial h with respect to y minus the partial g with respect to z, and that's in the I component. There we go. Right, and then plus, okay, the partial f with respect to z minus, this will be in the j component, the partial h with respect to x plus, last one, all right, the partial g with respect to x minus the partial f with respect to y. In the k component. All right, in other words, let's write all this out. So this is h sub y minus g sub z actually, let me make myself some space. This will be f sub z, this will be g sub x, minus, minus, and then it'll be h sub x and f sub y. All right, now, what would it mean if the curl was equal to 0? If the curl of our vector field was 0, that would mean h sub y minus g sub b was 0, which would mean h sub y equals g sub z. This should be setting off little bells in your head. Right? All right, that would also mean that f sub z is equal to h sub x, and g sub x is equal to f sub y, which is the definition we learned back on the first page of section 17.3. What would it take for, in 3 dimensions, for f to be a conservative vector field? This is what it would take, right? F sub y equals g sub x, f sub z equals h sub x, and g sub z equals h sub y, which is exactly where this came from. So we've already seen this before. If the curl of f equals 0, it means that f is source free, or excuse me, is conservative. Sorry, not source free, conservative. So I should put that on the other side, right? These 3 things being true means that the vector field is conservative, which is at the top of the next page. If your curl is 0, that means that you have a conservative vector field. Another term for conservative is irrotational. Right? Source-free vector fields are rotational. Conservative vector fields are irrotational. And that would mean that your circulation would be 0 on any closed path. All right, so let's put our newfound knowledge for how to find the curl for a 3-dimensional vector field into practice. All right, so we're going to find the curl of f. The curl of f is equal to the cross product of the del operator and our vector field, which is the cross product of del del x, or delta delta x, delta delta y, delta delta z, with x comma y comma z in this case, because that is our vector field. So x, y, z. Now we can do this 2 ways. We can rebuild what we just did. So I, j, k, delta, delta x, delta, delta y, delta, delta z, and then keep going to make the trick. And this is x, this is y, this is z, this is x, this is y. And so when we want to find the cross product, it would be the derivative with respect to z. So you can just kind of do this in your head. So the derivative with respect to y of z, the derivative with respect to y of z, because you're going this way. Well, the derivative with respect to y of z is 0. So that's 0. All right, go to the next one. The derivative with respect to z of x is also 0, plus the derivative with respect to x of y is 0. So you got a whole lot of nothing. Minus, and then the backwards way is going to do the same thing. The derivative with respect to y of x is 0. So 0k, 0I, because the derivative with respect to z of y is 0, and 0j. The derivative with respect to x of z is 0. So the whole thing is not 0, it's a vector, right? It's the 0 vector, right? But nevertheless, right, if the curl is the 0 vector, then that means that f is conservative. Or if you like, you can say irrotational. Oh, and there is a typo on the top of this page, and I should have said it on the previous page as well. The curl is a vector, so it should be a vector 0. Sorry about that, because each component is 0, right? It's not a scalar, right? It's not the divergence. Divergence is a scalar, so this should say the 0 vector right here. I'll try to fix that. I mentioned there was another way to find it. The other way would be to memorize this formula, right? So if you have this formula memorized, which comes from the original, so or if you find it first, then you can actually use it all the time because it works, right? H sub y was 0, g sub z was 0, so it became 0, 0, 0 for the terms. All right, let's do another example. So we want to find the curl of f. So we're going to take the cross product of the del operator and f, our vector field. Right, again, that's the del over the del x, del over del y, del over del z. Cross product with, oh my goodness, I actually should have an x there. It is a cross product. Right, so cross product with x squared minus z squared, 1, 2xz. All right, so I don't have that formula memorized, but I do know how to find a cross product. So that's what I'm going to do. All right, the first one's got the most to write. X squared minus z squared. This is just 1. X squared minus z squared. And then this is 2xz. Okay, so let's go in the forward direction. This way, and this way. All right, so the derivative with respect to y of 2xz is 0. So this is 0i plus 0i. And then the derivative of this with respect to z is negative 2z. Hey, that turned out to be something. And then the derivative of 1 with respect to x would just be 0. All right, so there's the 3 forward direction ones. Now let's do the 3 backward direction ones. So it's going to be minus something, and it goes k, then I, then j. All right, so in the backwards direction, the derivative with respect to y of that function is 0. The derivative of 1 with respect to z is 0. Oh, but the j term is going to work out. The derivative with respect to x of that is 2z. Okay, so the I terms combine together to make 0. The j terms are going to be something interesting. Negative 2z minus 2 more z makes negative 4z. And then the k terms turn out to be 0. So this is our curl. And it's a vector, and it's not the 0 vector. So therefore, f is not conservative. Or if you like, you could say not irrotational. Whereas up here, we ended up with the 0 vector, so f was conservative on that one. Right? 0 vector became our cross product. Down here, we have this vector as our cross product. That's not 0.